We all get impressed by bike stunts, don't we? Some of you might have tried them and would have failed miserably, injured yourself without understanding the physics. So have you thought about the physics behind these stunts? What are these bikers doing? You can explain them using your class 11-12 dynamics physics. So there are basically two stunts which impresses us the most. This one, where the biker lifts up the front wheel, basically resting on the rear wheel. And the second one is this one, where the biker lifts up the rear wheel. I'll first explain the first stunt, okay, where the biker was lifting up the front wheel and resting on the rear wheel. So what I have done is I have drawn a very rough sketch of the bike and the biker. The object, small m placed on the top, is actually the biker, okay? It's a little difficult to draw the entire biker. Now let's start with the very beginning, the most simple thing, where the bike is simply resting on the ground with the biker. In that case, what are the forces acting? The forces are the weight of the biker and the bike acting downwards somewhere from the middle. It would act from the center of mass. Let's assume that the center of mass is at the middle, okay? There would be a contact force at the rear wheel and another contact force at the front wheel. And all these forces would balance each other. I hope you can understand that if the biker moves backwards in such a way that the weight or the center of mass moves beyond the contact force N1 somewhere over here, then of course the bike would move up. But that is not something which is actually being done by the biker while riding it, okay? It's much more complex actually. Now, when the biker moves with a constant velocity, what happens is the forces are absolutely same. There is no other force. You may think, what is friction? See, I'm assuming that the biker and the bike achieves a pure rolling motion. There is no slipping. If there is no slipping and the bike is moving with a constant velocity, there will be no friction. So these are the three forces which would be acting even if the bike is moving with a constant velocity. The wheels would be rotating and the bike would be moving forward with a constant velocity. Now, in order to lift up the bike, there has to be a net angular acceleration in this direction. What the biker does is he increases the throttle, or he accelerates. He puts on the acceleration. You might be knowing that bikes are rear wheel driven. That is, when you apply the acceleration, you apply power to the rear wheel. So the rear wheel would get a torque in this direction, in the clockwise direction. That would cause an angular acceleration. Now, when there is an angular acceleration, at this contact, the wheel would be slipping because there is no enough linear velocity. So you end up with a frictional force at the forward direction. What is happening at the front wheel? Let's assume the ideal case, or just the moment when the rear wheel has started rotating with a higher speed. At this moment, nothing extra is happening at the front wheel. It's the rear wheel where everything is happening. You have a frictional force towards the front. You can see that the frictional force is providing an additional torque in the anti-clockwise sense, which may try to rotate the bike in the anti-clockwise direction. But that doesn't happen always. You, of course, accelerate your bike. It's not every time that the bike starts rotating. In fact, most of the time it doesn't rotate, only with specific actions that happen. So what is happening? Think. As soon as FF, that frictional force, comes and there is an additional torque, these two forces, N1 and N2, has a very interesting role. N1 and N2, you know, both of them are self-adjusting in the sense they can increase their values or they can decrease their values. And N1 and N2 would always try that the bike does not rotate. They try to prevent rotation. They can adjust themselves to stop the bike from rotating. And that can happen only if N1 goes up, because N1 is giving a torque in the clockwise direction, preventing the rotation. N2 is actually helping in the rotation, right? So N1 goes up. They are very smart. N1 goes up. Now, what happens if N1 goes up? If N1 goes up, you know N1 plus N2 is equal to capital M plus small m into G. And this balance has to be maintained. This balance cannot go away. So if N1 goes up, N2 has to come down, right? So N2 goes down. This is where the story ends in a normal case when you ride a bike. But what if we have a limiting case, or the situations are such that N2 reduces and becomes equal to 0? If N2 becomes equal to 0, the contact here is lost. If contact is lost, the bike is rotating, it's moving up. So N2 is lost. Now let's find out, when can N2 be lost? That is, the contact at N2 is lost, and when it is not lost. What is the special case? If N2 becomes equal to 0, the only torque acting on this bike in the anticlockwise direction is because of frictional force and N1. And we are taking the axis about the center of mass. Let's assume that the distance of the line of action of N1 from the center of mass is equal to x. That is, the contact point at the rear wheel is at a x distance from the center of mass. Also, let's assume that the ground is at a distance of y from the center of mass. In that case, the torque along the anticlockwise direction is Ff into y minus N1 into x. And if this is greater than 0, then the bike would move up. Can this be greater than 0? Of course it can be, but there are specific cases. See, Ffy has to be greater than N1x in order the bike to rotate. Now you know that frictional force at this contact has to be less than or equal to the coefficient of friction at that contact multiplied by N1. So can we say that mu N1 has to be greater than mu N1y has to be greater than N1x? N1 cancels out. You get mu y has to be greater than x. So x has to be such that it is less than mu times y. Only then the bike will rotate. Typically on the surface where those stunts are performed are concrete. In concrete, this coefficient of friction is around 0.7. So 0.7 y has to be greater than x in order for the bike to rotate. So you have to give a sudden heavy acceleration, and this frictional condition has to be met. First of all, N2 becomes equal to 0. N2 becomes equal to 0 when you have enough friction, such friction that N1 increases to a certain level that N2 becomes equal to 0, and then 0.7y or mu times y has to be greater than x. See, x can be reduced if the rider pushes himself backwards. If you look into those videos of stunts carefully, you would see that the biker is moving backwards. This reduces X and gives a higher chance of the bike lifting up. So this is the physics behind. Now an interesting thing I would like to discuss more. When the bike lifts up, is it an unstable case or a stable case? See, the dynamics are actually pretty complex, okay? What do I mean by unstable and stable? So that means if the bike is rotating upwards, would it continue to rotate up without any control and it spins? Or whether it is stable, that is, it moves up and then comes down. See, this whole thing would happen till the point when you have friction. When will friction cease to exist? When linear velocity v becomes equal to r omega, where r is the radius of the wheel. So everything has to happen very quickly. The bike is accelerating, so the angular velocity is there. Linear velocity is coming through friction, and friction would be there till the point v is equal to r omega is not reached. That is, v is less than r omega. Till that situation happens, there would be friction, there would be rotation, and the bike would move up. Okay. Of course, remember one thing: the friction, this condition that we have written, is the limiting condition. Okay. So limiting condition would not be always there. Frictional force would actually be lesser than this. So all these dynamics play into account. The bikers, of course, don't know physics. Or maybe they know physics, but not to this extent. They have experience. Through experience, they do it. And this is the physics behind. So we have understood what is the physics behind the bike lifting up and resting on the rear wheel. What about the other case where the bike becomes something like this? How is the biker achieving it? Let's discuss that in the next video. Okay. Thank you.